Okay, all right, so let's continue. Let's continue from where we left off, common emitter amplifier. And if you recall, we had a schematic. Let me draw it. We had a schematic of common emitter amplifier with the voltage divider bias. So we had RC, we had RE, we had R1, we had R2, and we had a coupling capacitor here. We apply the signal here. We have a bypass capacitor. CE, and of course there's a supply voltage here, VCC, and we can, of course, if we want, we can connect a load here, RL here, right? So that's the circuit that we had discussed, and we've seen how to all of you should know how to calculate the bias point, ICQ, VCEQ. That's the bias point here. Bias point here. All of you should note this. Once you do that, you should know how to calculate the small signal parameters. Small signal parameters like GM, R pi, GM, R pi basically, and R naught. And in high frequency, we know we have given you expressions to calculate C pi, C mu, all of these things here, small signal parameters. So that's something else that you should know. And from there, all of that, you should be able to get the open circuit voltage gain, input resistance, output resistance, lower cutoff frequency, upper cutoff frequency, and we'd also seen voltage swing, output voltage swing here. So you should be in a position to get all of this thing here, all of these quantities here, right? And we had also said that this amplifier that we have can be represented by, once you calculate, can be represented by, at least in the mid-band region, Rn plus minus AV0 dot Vin times R0. These values that you calculated, here, AV0, Rn and R0, you can make a new circuit which is of the amplifier, equivalent circuit of the amplifier. Okay, Rn here, the voltage here is of course Vin. Right. So this is important when you are, for example, a single amplifier stage may not be enough to provide you with the entire gain. You may cascade several amplifier stages here, and when you're cascading, this representation is what is required here. The other thing that we had said was, if we look at this amplifier, we had calculated, and I've asked you also to do in the homework, that AV0 Rn, and we saw that in the last lecture, R0 is equal to beta, right? So this is a sort of tells you the trade-offs that are there amongst the gain, input and output resistances that are there here. Okay, AV0, yeah, AV0 Rn by R naught equal to beta here. So if we look at a common emitter amplifier, so let me go to next. Let's write down common emitter amplifier. One of the characteristics of common emitter amplifier is AV Rn by R0 equal to beta. Right? So this is there. So if I look at my common emitter amplifier, Let's say we take beta equal to 100. Say beta equal to 100, right? So right hand side is fixed. So it allows you to now choose the values of AVRN and R0. So one possibility is, for example, if I choose AV0 of 100, by the way, this is AV0 of 100, Rn of 1 kilo ohm, R0 1 kilo ohm. I may design an amplifier like this, right? And it gives us 100. So with this in mind, many books, what you read is that common emitter amplifier with these kinds of numbers, common emitter amplifier gives you, so people take these as typical numbers, so they'll say it gives you high voltage gain, moderate input resistance, and moderate output resistance. People often take that as the characteristics of a common emitter amplifier. High voltage gain, moderate input resistance, and moderate output resistance. Okay, moderate meaning, as you can see here, a kilo ohm. By moderate, so these are subjective quantities. What do you mean by moderate? So moderate here, basically like a kilo ohm, 1 kilo ohm. It's like 1 kilo ohm, right? High input resistance, in contrast, if I take that as a moderate value, high input resistance would become maybe 100K or larger, 100 times larger. So it becomes a high input resistance in that context. Okay, low output resistance would become maybe 10 times lower, maybe 100 ohms, maybe 50 ohms. That would become a low output resistance here. Okay, so this is the often taken as the characteristics of common emitter amplifier here. But if you look at it, if you look at this expression here, there's nothing that is preventing me from designing an amplifier, let's say, with a gain of 100, with the input resistance of 100 kilo ohm, but with the output resistance of also 100 kilo ohm, and this is also equal to 100. It's also equal to 100. So in this case, what did I achieve? I achieved a high value here, let's say, I achieved a high value here, I achieved a high value here, and I achieved a high value here, right? I could design a common emitter amplifier like this. So so what I'm trying to say is that most books would say the signature of a common emitter amplifier, if we write it like this: voltage gain, input resistance, output resistance, the signature is HMM, high, with the idea that the first one denotes the voltage gain, second one denotes the input resistance, the third one denotes the output resistance. It's like HMM. Well, here we said, well, this is also possible, HHH. I could design with 100K. It does not violate this equation. I could design an amplifier like this, HHH. It's also possible, I could also think of a design, which is of this kind. 100, gain of 100, and input resistance of 100 ohms, and output resistance of also 100 ohms. That also gives me, that's also a possibility. And therefore, in this case, what I'm obtaining is H, maybe LL. HLL, right? So this is HLL. So the thing is that you should not think of a common emitter amplifier just in terms of maybe high voltage gain, moderate input resistance, moderate output resistance. That's one way of looking at it, but it's not a complete picture. Complete picture would be this: in terms of his input and output resistance capability, this is the complete picture. It says AV0 Rn by R0 equal to beta. You could design an amplifier with a gain of 100. There's nobody who's preventing you from designing an amplifier with a gain of 10. You could design an amplifier with a gain of 10. And I could do a gain of 100K. So then it doesn't become a high gain. It becomes a low gain. I could design an amplifier with a gain of 10. This become 100K. And this one maybe then how much? 10K. 10K. You could do that. So then it becomes a low gain, high input resistance, maybe high or moderate output resistance. So you have all these because there are trade-offs. There are different ways of designing a amplifier, and you have all these trade-offs that are there. Maybe most of the time you may design a common emitter amplifier with a high input and a moderate input resistance and a moderate output resistance. You may design it many times in this particular manner here, but you could design in this fashion also. You could design it in this fashion also. You could design it like this also, depending on what your needs are. You could design it in various ways. For example, continuing on the same line, let's say somebody wants a design like this. For some reason, let's say that we have a source, and the source resistance is say 5K, some high resistance here, and the load here, the load is maybe 100 ohms, and says design an amplifier which gives me overall gain of maybe AV equal to, I don't know, say 200, 250, or 250, let's say AV of 250. So this person is interested in designing an amplifier with a gain of 250, meaning this is V0, so meaning V0 by Vs, not open circuit but total overall gain, is interested in getting a gain of 250. Okay, he's not saying anything about input resistance or output resistance. He's saying, well, this is my source and this is my load RL, and I want a gain of overall V0 by Vs of around 250. Now, do you think a single stage amplifier will be enough for it? Single stage amplifier? One stage amplifier would be okay for it or not? Will it give me a gain of this thing? As an example, suppose you do think that, okay, maybe I can do it in one stage. I could do it in one stage. So maybe you're thinking, well, I'll put a common emitter stage here, and I'll satisfy the entire specs through a single stage amplifier. And by the way, the person also says that, VCC is 6 volt. I don't want to use, let's say, more than 6 volt. The whole system is running on a 6 volt battery or 9 volt battery or something like that. Right? So 6 volt. 6 volt single supply voltage. So do you think a single common emitter stage will do it? Single common emitter stage will give me this AV equal to 250. How would you design? Remember, common emitter stage, what is the equation that you have to keep in mind? AV0 Rn by R0 equal to beta. Let's say the common beta that we have available is 100. Okay, so beta, we have a particular transistor, the beta is 100 for it, and this thing here. So in order to design this amplifier, you have to decide, this person wants an AV of 250. AV of 250 means what? AV0 has to be 250. But remember what this amplifier is. How would you decide this? This amplifier will look like what? So if I were to draw this equivalent circuit, the whole equivalent circuit would become, right, if you say a single stage will work, Vs 5K, then this amplifier that you have will look like here. Remember, we said the amplifier can be represented by Rn and can be represented by AV0 Vin by R0 That's what your amplifier looks like, right? Amplifier looks like, and then you connect the load here, 100 ohms, RL, V0. This is the in. So we know that the gain of this particular stage would be how much? Would depend on overall gain. AV will be equal to Rn, easy to see, Rn plus 5K multiplied by AV0 and 100 ohms divided by R0 plus 100 ohms. Right? That would be the overall gain, and you're set that you want this to be equal to 250. So do you think it is possible? 250, to obtain 250. Right? Remember this constraint. This factor, what do you see? This factor is less than 1. This factor is less than 1. Okay? This factor is less than 1. This factor is also less than 1. Obviously AV0 has to be greater than 250. So can you suggest a design? How do I proceed? What if I choose Rn equal to 10K? Or Rn equal to 5K? As an example, suppose I start choosing something. Let's see. I start choosing, say I choose Rn equal to 10, let's say 5K. Rn of 5K. And let's say I choose R0 of 100. I choose, I have choice, I have to do. These are tentative. Design will never occur in one step. Design is always iterative. You try something, it doesn't work, you learn from it, you try again and all that. Suppose I use 5K and I use 100. Then this factor becomes half, this factor becomes half, and therefore this has to be 250 into 4. Right? A factor of 4. So this I will have to choose 10 to the power 3. Correct? 10 to the power 3, 5K and 100 ohms. Right? It seems like a design, but does it satisfy this constraint? Well, what does it give us? 10 to the power 3, Rn of 5K and over 100. And so what do I require? Right hand side tells me. So it tells me what? 5 into, not 500. 5 into, oh, so it says, well, you could do it with a single stage common emitter amplifier, provided you had a beta of 50,000. Beta of 50,000. We don't have a beta of 50,000, right? We have a beta of 100. Well, obviously this design will fail. I can't do it with a single stage common emitter amplifier. Now you could try different stages. Well, you'll say, well, let me not use 5K. What do you want to use? 10K? 100K? You can try different combinations. You could make this as 100K, you could make this as something else, and you will check that no matter what you do, you will not be able to do it. You will not be able to do with a single stage. Right? Single stage amplifier, you will find that the task is such that I will not be able to do it with single stage. Then you say, okay, if single stage fails, then let me do it with 2 stages. Let me do it with 2 stages. Alright, so what you would do, the design task will become, well, single stage is failing, so let me remove this, let me add here, maybe 2 stages here. Let me add here another stage here. If single stage is failing, let me add another stage here. another stage here. Another stage here. Okay, all right. This is, let's call this CE1 and CE2. On the same supply voltage, let's run it. Two-stage design. Now, do you see an advantage of using a two-stage this thing? I'm no longer limited by AV0 Rn by R0 equal to beta. Right? I'm no longer limited by that, because this stage has to satisfy this, and I have this stage also satisfying this. I have more capabilities now, right? I have more capabilities now. So when you look at this particular stage here, you would see that what should I try to do with this stage? If I focus on the first stage here, maybe what I should try and do is, with the first stage, I should try and get a large input resistance, right? Because note that when you build an amplifier, you get a loss Rn by Rn plus 5K as it goes through. So maybe what you should do is try and use a large Rn in this stage. But note that when you use a large Rn, when you lose a large Rn, then you lose R0 and you lose AV0. You will lose that large Rn value, right? You will lose that to some extent. When you look at this stage, you will look at this stage interfaces with the load, and with the load this term comes in, 100 by R0 plus 100. So you will say, well, for this stage maybe I should use R0, which is small, R0 small and Rn large. You would design this particular stage with a large Rn, because Rn should be maybe much larger than 5K. Maybe you'll design it with a 50K. And here R0, so you will design it with not maybe 100 ohms, maybe we'll design it with 50 ohms or whatever. There's something here. Because this interfaces with the load, and with the load this term comes in. This term comes in with the load. Right? So we have a different designs here. Right? So we have different designs for, so note that each common emitter amplifier will not be designed in the same manner. This common emitter amplifier you will build in a large Rn. This common emitter amplifier you will build a small R0. Right? Now you may find that maybe two stages are not enough. You may find that two stages are not enough, and you may require a three-stage amplifier. Right? So you may want to add another stage here. Three-stage amplifier. Let's call this CE2, let's call this CE3, and maybe CE1. Now, when you add a three-stage amplifier, it gives you more freedom. This stage will what will it do? It will specialize in giving you large Rn. This stage will specialize in giving you small R0. You'll focus on providing small R0 so as to match with the load. And while the middle stage, you'll go ahead and focus on providing a gain. Right? So many times what happens is, from a one single amplifier, see, normally what happens is, I mean, in the sense if somebody is asking you in a good design, let's say, somebody says like this, right? Let me draw this again, Vs and 5K, and says design an amplifier, and the load is 100 ohms. Well, many times what we think is, well, we should design this amplifier such that when I look from here and says give me a gain of 250. So anyway, gain is specified, 250. So when I look from here, what I should do is I should make Rn much larger than Rs, so that the entire signal that you see here goes into my amplifier. Right? I should make Rn much less. So I need an Rn of maybe at least 10 times higher. So 10 times higher is 50K. Maybe I'll use 100K. Now also, this is the output resistance here. So you want output resistance to be much smaller than 100 ohms. So maybe I'll use R0, which is, let's say, 50 ohms or even smaller, right, compared to the load resistance here. maybe even smaller, 20 ohms, 25 ohms and all that. So note that I require a small output resistance smaller than the load. I require a large Rn. Now, and on top of that, I require a large gain. So asking one single stage, asking one common emitter stage to give a large Rn, to give a small R0, and to give a large AV0, it's not possible. We saw that AV0 Rn by R0 is beta, is 100, let's say. It's not possible. A single stage to give you everything good, AV0 also high, 250, Rn also 100K, R0 50 ohms, is not possible. It will not be able to give you. That's why you have to go to multi-stage amplifiers. You have to go to multi-stage amplifiers. So rarely would your requirement be such, that the requirements are so simple that with one stage you just do it. Most of the time the requirements would be such that you have to put several stages together. Okay, several stages together in order to build in order to satisfy the specs that are there here. Now in this context, while common emitter amplifier is fine, is one particular stage here, there are other amplifier stages also. So other amplifier stages. One of the amplifier stages we saw was common collector, which was part of homework, common collector. Common collector amplifier. This is a useful amplifier. You'll see in a minute in our discussion. So this is, we were drawing like this. There are various ways of implementing it. We are implementing it using the same bias strategy. Signal is applied at the same place. Vs here. Now, except that we don't take an output at the collector, we take an output at the emitter. Here, we may connect a load here, RL. And this becomes a common collector amplifier. Common collector amplifier because the collector node, when you do a small signal analysis, the collector node becomes a ground node. Okay? Now this particular stage, let's all of you should be in a position to calculate the bias point. It's the same way that we calculated earlier, right? The bias point could be calculated in the same manner here. In the same manner that we had discussed, you should be able to calculate the bias point. R1, R2, RE, RL. Okay, as an example, let's say, suppose this is 6 volt. This is 6 volt, and we want output at this point here. So let's say I design it in such a way that, for example, I'm just saying, let's say this is 1 kilo ohm, and we design it such that the voltage, DC voltage here is 3 volt. 3 volt. So we are talking about emitter current or collector current or ICQ of 3 milliamperes. 3 milliamperes here. So this is 3. So a particular design I'm describing, just so that you get an idea about the numbers. Say I design it for 3 volt here, so that we get a 3 milliampere current here. If this is 3 volt, this becomes 3.7, and we have 6 volt here. 6 volt here, right? And we want R2 by R1 plus R2 equal to R2 by R1 plus R2 equal to 3.7 by 6, right? So that gives you one constraint in the design, because this is the voltage divider. The other thing that we said was that VCC by R1 plus R2, the current flowing in these branches should be much larger than IB. IB would be 3 milliamperes, so if we take beta equal to 100, so this should be much larger than 30 microamperes, right? 30 microamperes, so much larger, take at least a factor of 10. So anyway, on that basis we will get some value of R1 and R2, right? So let's look at some R1 and R2 which you can calculate. Okay, so this is our amplifier. For the sake of argument, let's take RL equal to also 1K. Okay, for some values here. Anyway, so it is biased at ICQ equal to 3 milliamperes, and VCEQ is biased at 3 volt. That's what we have biased it. Now, what we are interested in is knowing the voltage gain. Voltage gain, input resistance and output resistance. So this is a part of the homework problem. Similar thing was there in homework problem. So how do we calculate the voltage gain, input and output resistance? So in that context, what I want you to remember, we have done this before. I want you to remember the following results. So there's a result that, if you recall, when you take a transistor, say there's a transistor like this, okay, or let me put it like this, all here. When you look at this here, here's a transistor. Now this, what I'm talking about is small signal analysis, okay? Remember this. So this transistor, small signal analysis. So this transistor is already biased. I'm not showing it. The transistor is already biased in active mode. Biased in active mode. Transistor is already biased in active mode. Now I'm going to ask you now a certain set of results, okay? So if I take this transistor, okay, this transistor is already biased in active mode, okay? So consider the following. The same transistor, let's say this same ground, doesn't matter what the voltage is here, it doesn't really matter. And suppose I ask, what is the resistance looking from here? When I look at this transistor, this is ground, and when I look from the base, how does it appear? What is the resistance that I see? There's nothing here. The ground, small signal ground. Huh? R pi, correct. It's simply R pi. Remember that. What is the resistance looking from here? When I look from the collector? Not infinite, R0. R0 may be large, but it is R0. So when you look at it from the collector side, it is R0. When you look at it from the emitter side, it is R pi. Okay, important result. Suppose I modify this. If I modify this to the following. This is important for us. I add here, what is the resistance looking from here? Let's say this is RE. These are all small signal. Never forget that. These are all small signal. What is the resistance looking from here? R pi. 1, if you want to be more accurate, 1 plus beta RE. Whatever is the resistance here, when you look from here, it gets multiplied by beta, 1 plus beta. Okay? This resistance also increases, but is less important for us. This also increases, it also gets multiplied by R naught, beta and all that, but it's less important because it's high anyway. Okay? You can also derive that. The other important result for us is the following. Doesn't matter what is here, but say this is some resistance here, Rs. What is the resistance looking from here? When you look into the emitter, what resistance do I find? When you look from here, the resistance is R pi plus Rs divided by 1 plus beta. When you look from here, this between here and here is R pi plus Rs, and we said, remember in very first lectures we had seen all those, that it gets divided by beta depending on where you're looking from. So these are the results that you must remember. R pi, because it will help us simplify the analysis. R pi, R pi plus 1 plus beta, and this result here. Okay? And with these results, you will see that very quickly you can calculate everything about a common collector amplifier. The calculation of common collector amplifier would become very simple. So keep these things in mind. Okay? So common collector amplifier, let me draw it again. I have to keep drawing again and again. Well, common collector amplifier. So I'm drawing now only the small signal part here. Capacitors act as short, RL. So this is V0. The small signal part will become like this. Please verify that the circuit that I drew becomes like this. Small signal circuit, R1 parallel R2. And then we have here Vs. This is Re. Our circuit, go back and see the circuit. This circuit that I drew becomes, capacitor becomes a short, this becomes ground, R1 becomes parallel R2, it becomes the circuit that I drew. So if you look at this one, if I want to calculate V0 by Vs, right, this is my goal, V0 by Vs. So when I see from here, the whole thing, what does the circuit appear to be? It appears to be this, between here and here is what? R pi, and this resistor becomes multiplied by 1 plus beta. So it appears to me, if I look from here, it appears to me as if my circuit is like this, as if there is an R pi, and this resistance that you see here, it appears as a 1 plus beta times Re parallel RL. This is this node here. Right, when I see from here. And this is the place where I take V0. So V0 by Vs then becomes, as you can see here, 1 plus beta Re parallel RL divided by R pi plus 1 plus beta Re parallel RL. We can immediately get the gain of this amplifier. This whole circuit between here and here is R pi. Between here and here is R pi. And from here, this resistance is Re, but from the base side, it appears as 1 plus beta Re parallel RL. It becomes 1 plus beta gets multiplied. Re parallel RL you can all see here. right? And this is the output node here. So that becomes my gain. And then gain, as you can see here, the gain is less than 1, less than y equal to, it will never be equal to, so it will always be less than 1. So there's no voltage gain here. There's no voltage gain. But note that the quantities, we can take the quantities that we put. We had put here, we can calculate. We had put here 1K, we had put here as 1K, and R pi for us was, it was biased at 3 milliamperes. So R pi is VT by ICQ times beta. So R pi for us is about 2.6 kilo ohm divided by 3. So roughly a kilo ohm, 0.8 or 0.9. So you can easily verify that if you do this term, if you look at this term, RE parallel RL is 0.5K, 0.5K multiplied by 100. 0.5K multiplied by 100, so this gives us 50K roughly. And this R pi is about 1K here. So you can see the gain is very close to 1. Precise value of gain you can calculate, but you can see that the gain is fairly close to 1. 0.9 something. Right? The gain of this such a stage is basically equal to very close to 1. Now, because the gain is V0 by Vs is approximately equal to 1, this stage is also called, as you can see here, emitter follower. The emitter voltage, output is what? Output is at the emitter. The emitter voltage, it simply follows the input voltage, because V0 by Vs is 1. The output voltage follows the input voltage here, or the emitter voltage follows the voltage applied here. So that's why the word emitter follower. The emitter follows the voltage applied at the input here. It's called an emitter follower. Okay? So gain is 1. Gain is practically equal to 1. It doesn't provide you with gain. Its usefulness lies somewhere else. Its usefulness lies in Rn and R0. That's where the usefulness of this amplifier lies. Right? So we can write down Rn and R0. We have the circuit before us, and we can write down what is Rn. Rn, resistance looking from here, will be equal to, we have seen here, R pi 1, I'm going to 1 plus beta Re parallel RL. That's the resistance looking from here, between here and here, and this comes in parallel with R1 parallel R2. So the whole thing in parallel with R1 parallel R2. Right? So that gives me the input resistance. Now note that input resistance in a common emitter amplifier, the input resistance was simply this term, common emitter. This was only for common emitter. Now in common collector, we have this additional term. And this additional term, as for example, if I take 1K here and 1K here, and you multiply it by this is like 50K. And this is like 1K. So you can clearly see that the first term, this term is much larger as compared to R pi. But of course, to take advantage of this high term 50K, you have to make R1 parallel R2 also high. You'll have to make that also high. Otherwise, if you don't make that high, then the entire advantage of this term will get lost. So you'll have to make this term also high. And that can create potential problems, but we'll not go into that. But you can clearly see that Rn for this amplifier is high. If somehow this term you could make large, then you could see that this Rin for this one is going to be, in this example, is 50 times higher than this example. R pi would be 1K in the common emitter amplifier biased at 3 milliamperes. Rn is 51K. You can see much higher Rn. So that's one of the benefits of this amplifier. Very large input resistance. We had seen in an earlier lecture, it's not just the gain of an amplifier which is important. Rn is also important and R0 is also important. Right? So Rn is clearly superior here. Now same if you look at R0. R0 is resistance looking from here, R0. And if you just go back and look at this, resistance looking from here, use this result. If you use this result, R0 we can write as RE is there, parallel, basically R pi by beta, 1 plus beta. R pi by 1 plus beta. If R pi is 1K and beta is 100, so this term sort of becomes 10 ohms. Look at that. 10 ohms. R pi was approximately equal to 1K for us, in fact less than 1K, and divided by beta it becomes 10 ohms. That's the output resistance here. So here is an amplifier which gives you no gain. Rn is high. Rn is high and R0 is low. R0 is low. So this is our common collector amplifier, and we'll not go into the details here. The other part is frequency response is very good. Frequency response is very good. Very good. What do I mean by that? Upper cutoff frequency FH is high, is very high. So it's a very good amplifier in terms of frequency response also. For frequency response, we'll have to put in the C pi and C mu and then look at the cutoff frequency. We'll not go into the details of that, but the frequency response also comes out to be very good. So in all respects, it's an excellent amplifier. Very good frequency response, very good input resistance, very low output resistance, except that it doesn't give you gain. It doesn't give you gain. All right. So its advantage becomes specially that, you know, if you go back, let's look at the common emitter amplifier. What does it give you? If you think about it, gives you gain and doesn't give you very good values of input and output resistance, right? Common emitter, right? Suppose I want to make my common emitter amplifier, good overall amplifier. So common emitter by itself will have problems in giving you gain and high input resistance and low output resistance. It will have difficulty. But then suppose I now take my common emitter amplifier and I add a common collector stage. Together, what will they give me? Together, what will this amplifier give me? Common collector followed by common emitter. High input resistance and common emitter will give me high gain. Output resistance is still limited by common emitter stage, right? So this amplifier will have now two things in favor of this amplifier. Okay, as compared to, so let's see. Suppose we had an amplifier like this, original common emitter. So we had two things. We had AV going for it, Rn and R0 we had trouble if we try to do this. Now for this amplifier, AV is okay, Rin is also okay, but we have R0 sort of problem because it's still common emitter, right? How do I further improve things? How do I further improve?
Add another CC.
Yeah, so we could do this CE, and we said add a. So CC here was helpful, and then add another CC here. Now what will you have? So you all see the advantage now. We have AV, it gives you good. Rn, it gives you good. R0, in some sense, it gives you good. It's sort of becoming a complete amplifier now. A combination of common emitter, common collector at the input, common collector at the output also, now is giving you all the nice properties. AV is good, Rn is good, R0 is good. All of these things that are there. So you're seeing a strategy for building a better amplifier by using the common collector stage here. Common collector stage is to provide you with high input resistance, common collector stage is used to provide you with low output resistance, and in between putting common emitter stages to give you the gain that is there. And if one stage of common emitter is not good, you could build like this. So you could build an amplifier like this. You could build here, here, here. You could build like this, right? Build this as common collector, build this as common collector, and maybe build two common emitter stages, CE1 and CE2, right? CE1 and CE2, to provide you with a high gain here, and to provide you with input resistance here, to provide you with an output resistance here. Right, so very useful stage, common collector. The next stage is the common base stage here. So our common base stage, if we draw the same amplifier, we put a ground this here. You can see why later on we ground it here. VCC here, and in this case we apply signal at the emitter in the common base stage, Vs, and we take output at the here, V0. This is a common base stage. I've asked you to show, I'm not going to do that, I've asked you to show that as part of the homework, that when you look at the gain here, AV0, it turns out to be plus GM RC. If there is a load, then you will put GM RC parallel RL. If there's a load, then maybe you put an RL also, if there is a load here, okay? Plus GMRC parallel RL. Output resistance looking from here is straightforward, just like these things are just like the common emitter. Very similar to the common emitter. Remember common emitter, let me write it down. Common emitter, if I were building, it would have given me AV0 equal to minus GM RC parallel RL. It would have given me R0 also equal to RC, and it would have given me Rn equal to R pi. That's what it would have given me. This is also common basis, very similar, AV, except for no phase difference, positive here, GMRC parallel RL, R0 equal to same, RC. Rin is where you you get into a sort of a problem, Rn. When you look from here, this is the input resistance because you're applying the signal here. So when you look from here, you get Re parallel. Now note that this point, when you do small signal, this point becomes ground. This point is ground and this point is also ground. So R1 parallel R2, they all become ground. R1 gets shorted out, R2 gets shorted out. So the only thing when you look from here, you get R pi, so it's Re parallel R pi by beta, 1 plus beta. So its output resistance is basically equal to R pi by beta here. So if you look at the characteristics of common base amplifier, it can give you similar gain as common emitter. It can give you similar output resistance as common emitter, but its input resistance is very, very small. Right? And in this case, we had seen that that if you take, if you multiply AV0 Rn by R0, this is equal to beta. There's a signature of common emitter amplifier. In this case, if I do that, in this case, if I do AV0 Rn by R0, so remove RL for a moment. RL is not there. So by the way, so RL is not there. RC only is there. AV0 Rn by R0. This you see is equal to 1. So you compare the two. Okay, so let me write down both of them. Common emitter AV0 of common emitter, Rn of common emitter, R0 of common emitter equal to beta. AV0 of common base, Rn of common base, R0 of common base equal to 1. If I combine both of these two equations together, I can get AV0 common emitter by AV0 common base multiplied by Rn of common emitter by Rn of common base multiplied by R0 of common base by R0 of common base equal to beta. Look at this comparison between the two amplifiers, and what can you tell about the two amplifiers? Common emitter versus common base. There are several ways of looking at this amplifier, right? The traditional way of looking upon this amplifier, comparison of common emitter versus common base. The traditional way of saying is, well, if you take this ratio 1, both give you the same gain. Both give you 1. Then what can you say? Suppose I designed both the amplifiers with the same gain and with the same output resistance. Then what can we say as a comparison between them? Common emitter will give you a input resistance which is beta times higher than the common base amplifier, 100 times higher input resistance. Or you could say, well, I will make, you could also say I will make this equal to 1, and you'll say, well, maybe in some design, let's make this equal to 1. Then what is the advantage? Common base amplifier will give you 100 times higher output resistance. 100 times output resistance meaning it's a bad thing, right? So either way you see, common emitter is superior. Either it will be superior in terms of output resistance, or it will be superior in terms of input resistance, or it will be superior in terms of gain. You can see a comparison between them. Common emitter versus common base, right? Common emitter versus common base. You can see clearly that in terms of gain, input and output resistance, this amplifier common emitter is superior. So why would we use common base? We found an advantage of common collector. We found common collector is a very useful stage. But what about common base? We don't see any advantage. In terms of gain, input and output resistance, we see no advantage of common base. In fact, it's inferior by an amount beta. Either the gain will be smaller by beta, or input resistance would be smaller by beta, or output resistance will be larger by beta. You can clearly see a comparison. So the advantage of common base does not come in terms of AV0, Rn or R0. These are not the advantages. These are actually inferior things. The advantage of common base, advantage of common base is in its superior frequency response. Superior upper frequency response. By that I mean upper cutoff frequency. Superior frequency response. That's where the advantage of common base lies. In its superior frequency response. Okay, now why? Okay, we'll not go through a quantitative analysis, but you could see the reason here. Let me draw a common emitter here for you. The small signal part of common emitter. Small signal part of common emitter. Right, this is this common emitter, small signal equivalent circuit, common emitter. And let me draw for the common base part here. Common base is here. In this case also, output is taken here, RC, and common base here. This is where we are applying the signal, and this is ground. This is the common base part here. Now, if you recall, frequency response depends on basically frequency, upper cutoff frequency. So when I say frequency response, I mean upper cutoff frequency, okay? Not the lower. Lower cutoff frequencies are maybe similar. That's not the critical thing. Upper cutoff frequency. Upper cutoff frequency, okay? So here is where you take output, RC here, okay. Now in this, Now remember that frequency, when you think of upper cutoff frequency is fH. Think of it like this: 1 by 2 pi sigma RC, sigma R effective, C effective, basically. Cutoff frequency is nothing but 1 over 2 pi RC. If I have several capacitors, I'll have several time constants. So think like this. Cutoff frequency depends on this. Okay. Now, one of the issues with this amplifier, common emitter, is the following. Between here and here, we said there is a capacitor called C mu between base and collector, right? C mu. And if you recall, when we apply Miller's theorem, what happens to C mu? When I look at apply Miller's theorem to it, the C mu here, which is there between base and collector, right? C mu appears as if you take C mu out, and it appears as a capacitor here. Appears a capacitor here, C mu multiplied by 1 minus AV, the gain of the amplifier. So C mu could be 1 PF. You're building a gain of 100. It appears as a 100 PF capacitor. And if capacitor becomes large, note that the frequency becomes small. Large capacitor, if it appears at the input or output or whatever, you have to charge and discharge the capacitance, it becomes slow. In contrast, if you look at this one here, C mu, where is C mu connected? C mu is between base and collector. Where is it connected? Between here. One end of the C mu is what? Ground. There is no Miller's effect here. It's not getting multiplied. Miller's effect only comes, if you recall, Miller's effect only comes when I have an amplifier and there's a capacitance connected between input and output. Then this capacitor gets multiplied by the gain of this amplifier here. Miller's effect says this, that effectively you can take this capacitor out and you can put it here and you can put it here. This capacitor here. This capacitor in the feedback part. This capacitor is CF multiplied by 1 minus AV. And this capacitor is practically equal to CF. So that doesn't matter. So if there's a capacitor between input and output, there is no capacitor between input and output here. There is C mu and then there is C pi. So this common base amplifier does not suffer from this Miller's effect that you're seeing, this Miller's multiplication of capacitance. There is no this C mu or capacitance which is getting multiplied by the gain and therefore appearing as a large capacitor and causing a deterioration in upper cutoff frequency. For example, let's say the gain here is, right now the gain here is, let's say, minus 50, right? Now, and say the gain here is 50 also. Gain is 50. Now, if I make the gain 4 times higher, 200, what would happen is, as you make the gain 4 times higher, the capacitance will also becomes 4 times higher. While here, no such thing happens here. Here, no such thing happens here. The capacitance doesn't get multiplied. There's no multiplication. No such thing happens here in common base. So this Miller's effect, Miller's multiplication is absent in common base amplifier. And that's the source of a better frequency response in common base. Okay? So that's the advantage of your common base. There's no Miller's multiplication in common base. Gives you a superior frequency response. And note that it gives you a superior frequency response and it gives you a gain also. It gives you gain. AV equal to same gain, GMRC. This gives you AV equal to minus GMRC. So what you're saying is, here if you try to increase the gain, the capacitance also increases and frequency goes down. Here if you try to increase the gain, the capacitances are not increasing. The capacitances are not increasing. First order is not increasing. Okay? So that's the superiority of a common base amplifier. Okay, so if I now sort of let's summarize then. Common emitter versus common base. All right. What is in favor of common emitter versus common base? What would you like to say when you're comparing the two? What would you like to say about the common emitter? Let's just list the advantages and disadvantages.
Cutoff frequency dependence.
Common base advantage? No what? No Miller multiplication of capacitance, right? No Miller multiplication of capacitance. Basically C mu. C mu, better frequency response. Better frequency response. That's the advantage of this one. And what is the advantage of this one? Huh? Better RN, or basically this, right? We can write it like this: AV RN by R0 equal to beta. That shows a superior response. While here, AV Rn by R0 equal to 1. So this shows us the benefit here of common emitter. In a way, many times, so for a comparable gain and output resistance, what we can say is Rn is higher here, higher, or Rn is lower here, Rn is low here. Right, so that's the sort of comparison that we are building in terms of common emitter versus common base. Now you can see common base is a nice amplifier, but it's difficult to use, right? Except in some rare situations, it's difficult to use. Look at, suppose I have a common base amplifier. Let's take a common base amplifier. Common base amplifier we are saying is AV Rn by R0 equal to 1. As an example, let's say we build AV equal to 100, R0 equal to 1K, and then Rn will become 10 ohms. All right. Here is an example of common base. Right? Common base. Now, how do I use this amplifier? Let's say I have this common base amplifier with these kind of characteristics, right? And I connect it to, my load is, let's say, Vs, and the load is, say, 100 ohms. Not a very high, so input is not a very high input resistance. Rs equal to 100 ohms. And I put load of, let's say, 1K. What do you think will be the gain here? V0 by Vs would be how much? What do you think will be V0 by Vs if I use a common base?
Around 25.
Because you have 100 and you have 10. So you have factor of 10 attenuation. The signal, because the input resistance is 10 ohms, so the signal is going to get attenuated by a factor of roughly 10. So gain would be roughly 1/10, and there's a factor of half and 100. So it is 5. The gain would be only 5. Right? Only 5. Why? Because this entire signal that you see here, if you have 10 millivolt, 10 millivolts sine omega t. 9 millivolt will drop here, only 1 millivolt will appear here. Because of the very small input resistance here. Input resistance is only 10 ohms. So it would be very difficult unless your source, unless the source happens to be a very, very low resistance source, you can't use this amplifier. Everything is getting the signal, entire power of the signal is getting dropped across the source resistance. You can't use it. Of course, how can you use, if you want to use common base in a meaningful manner, what can you do? What can you do? Well, you may think, well, before common base, why not use it? Maybe you may think like that I will not use common base here. Maybe I'll use a CC stage here, right? I'll try and use this stage here. So sort of this builds up, this gives me a high input resistance, and but note that the output of the CC is what? CB, right? Output of CC is CB. So there again you may face a problem. See an example. Let's take an example. Same common base. So common base is what? AV0 equal to 100, R0 equal to 1K, and Rin equal to 10 ohms. Let's take a common collector amplifier. These are common base. Common collector amplifier. For this we'll take a gain of AV0 equal to 1. We'll take an Rin equal to 100K, and let's take R0 equal to 100 ohms. If you connect a common collector like this, you think the problem is completely resolved. It is better if I use a common collector versus common base, right? Well, put here again 1K and put here 100 ohms. Yes. What do you think will be the overall gain? V0. Huh? Same what?
The gain as previous one.
No, I don't think so. That's not true. Not true. What will be the gain here? Well, how would you do this? We have to, as usual, what we do is we build our equivalent circuit. So this is like this. 100 ohms, common collector amplifier, build this Rin, build this gain, build this R0. So Rin is 100K, gain is, we'll take it as 1 times V in, R0 is 100 ohms. Then you put common base is here, is only 10 ohms, and then you put here plus minus here, you put here common base is, output is 1K, and then it's connected to 1K here. This is 100 here. Times V01, This is V01, right, like this, right? The circuit it goes. Now if you notice something here, the signal starts here, Vs. The signal starts here, Vs. And almost because this is 100 ohms, this is 100K, the signal appears here. The same signal appears here, right? Vs. So the signal here is also Vs, right? Because the same signal is also Vs here. You get Vs here. Now this is 100 ohms and this is still 10 ohms. So the signal sort of gets attenuated again. 110. The signal gets attenuated by a factor of 10 here. Factor of 10 here, and then there is an attenuation of factor of half here, and accordingly then you can see. Okay. So you know the common base has such a low input resistance here that unless the common collector's output resistance matches this, so you have to build a common collector amplifier such that is also 10 ohms maybe, right? 10 ohms, then maybe you know you could build a higher gain amplifier here. The way common base amplifier is commonly used is in this configuration. Use of CB amplifier, common use of CB amplifier. Common use of CB amplifier is like this here. Surprisingly, you'll see that I use it like this: CE followed by CB. The idea behind this is that don't use CE alone. The idea is don't use CE alone. Use this. Use this strategy. A CE followed by a CB. This pair is, the idea is superior to a common emitter amplifier. CE followed by CB as compared to a common emitter amplifier. Okay, how? So this amplifier goes by the name cascode amplifier. Together, we'll see how you can connect CE and CB together. The two CE and CB stages are fused together, right? Here it appears to be a separate CE stage and a separate common base stage here. But what we are going to do is we'll take these two, we'll take common emitter and common and fuse it together, fuse them together into one single stage, which we call as a cascode amplifier. But what is the idea here? See, the idea behind this is the follows. Let's take a common emitter amplifier. Take this common emitter amplifier, right? This common emitter amplifier has a problem of C mu, right? Remember, C mu is connected between, in a common emitter amplifier, this is base and this is collector. And the problem is that between the base and collector, there is C mu which is getting multiplied by the gain. That's the problem with common emitter amplifier here. But common emitter amplifier gives you a reasonable Rn. Reasonable Rn and all that, right? Now, if you look at this particular stage, common emitter. So now what we are saying is, okay, so common emitter has this problem. So what we do is we follow it by a common base stage here, right? Common base stage here. Now base stage meaning that this is now the emitter and this is the collector. In a common emitter, this is the emitter. Common base stage. So this is common emitter and this is common base. So this is the emitter node and this is the collector node. And this is the base node here. And in this case, this is the emitter node here. Emitter is common. So now what happens? Now what happens is, if you look at it, this common emitter, what is the load of common emitter? The load of common emitter stage. Remember, the gain of common emitter is what? The gain of common emitter stage is, we said, minus GM RC parallel RL. Okay? That was the gain of the common emitter stage. Now, if I look at this common emitter stage, what is this load? Load of common emitter stage is what? The Rn of common base stage. So RL of common emitter is actually Rn of common base, and which is equal to what? We said is equal to R pi by beta. So when I connect like this common emitter to common base, what happens to the gain of the common emitter stage? AV becomes minus GM, AV of, I'm talking about common emitter, AV of common emitter, AV of common emitter, AV of common emitter, okay? Minus GM is RL is so low, R pi by beta, so RC doesn't matter. So it's basically equal to R pi by beta. And this is nothing but equal to minus 1. So the gain of the first stage becomes 1. Common emitter amplifier I've used, and its gain is what? 1. Why? Because its load is so low. The load is so low here. The load that we have is so low, R pi by beta. So the gain of the first stage overall, even though you may, AV0 may be 100, open circuit voltage gain may be 100, but when you connect a load which is so small, the gain becomes 1. So remember, what was the problem with the common emitter stage? The C mu was getting multiplied by C mu 1 minus AV, was getting multiplied by 1 minus AV. Now what is the gain of this particular stage? 1. And is getting multiplied by how much? Minus 1. So it's getting multiplied by a factor of 2. It's not getting multiplied by a lot. So Miller's multiplication is gone. So if you look at this particular stage here, you applied Vs here, right? What is the voltage at this node then? At this node, what did we find? AV is minus 1. So the voltage at this particular node is between here and here? Oh, yeah, minus Vs. Instead of Vs, minus Vs. And this voltage now goes to the common base. And what does the common base do? Put an RL. The common base gives you a gain of how much? Plus GMRC. GMRC parallel RL. So overall gain, what happens? Overall gain, V0 by Vs is plus here, minus GM RC parallel RL. So what benefit have you, our earlier common emitter stage, if I had directly connected to my load, if I had taken common emitter and directly connected to a load, right? Directly connected to a load, it would have given me minus GM RC parallel RL. Now I connect a common emitter and I connect a common base together, I still get minus GM RC parallel RL. What did I gain? Compared to common emitter, I didn't get the Miller's. See here, the Miller's capacitance would have gotten multiplied by 100, by the entire gain. Here it is getting multiplied by just 2, by just getting multiplied by 2. It's just getting multiplied by a factor of 2, that's it. And here is getting multiplied by a factor of 100. So in a way, I've gotten rid of Miller's effect. I'm getting the gain also. I'm getting the gain also without the Miller's effect problem here. My C mu getting multiplied by the gain of the amplifier. So this is a strategy that is used where common emitter followed by a common base stage is used for constructing the amplifier. To make a amplifier which gives you gain as well as high bandwidth. Okay, so it's used to get high gain and high bandwidth. High gain and high bandwidth. That's what one is trying to do through this. Take a common base stage, common emitter stage, and follow it by common base stage. So who is actually building the gain? The gain is being built by common base. Common emitter, what is it doing? Is providing the input resistance. Common emitter is providing you with the input resistance here. It's providing you with the input resistance, and together they are building a amplifier here. All right. So this is what we call as a cascode amplifier. So cascode, the idea is that what we are going to do is take a common emitter and connect it to a common base. So we are talking about this. But as I said, we are going to take these two and actually fuse them together. Fuse them together. Fuse them together. I'm not going to make them as a common emitter stage, full common emitter. See, normally you would think of doing this like this, right? You would think of doing like this, common emitter. You would say here, here, here. One would like to build it like this, full, I mean, normally one would say, okay, take the output here, then connect it to the common base stage here, right? So common base stage, let's say we connect it like this. Is connected to the output here, here, here. This is the common base stage here, right? So this is how this common emitter and this is common base, right? We are thinking that would be a simple connection. That would be a simple connection. You can short all that VCC here and all. So you have to build all these things here. So the idea is, why do all this? Why build R1, R2 and all that? Can we share components? So see if this makes sense here. So the idea behind this is that we do the following. So here is my common emitter stage here. See how we are fusing them together. Common emitter stage, fine. Normal common emitter stage. This is, let's say, Q1. So Q1. This is my common emitter stage here. I'm going to use just like a capacitor here. Somewhere there would be a capacitor here. We'll apply the signal here, Vs, right? And of course I have to bias it together. Now where does the output of the collector go? Into the, note that the collector of this goes into the emitter of the next transistor, right? To the emitter node of the next transistor. So what I do is the following. On top I put the second transistor, this Q2. Right? Note that Q1 is going into Q2 and there's a capacitor that was used here, but I remove the capacitor, I directly couple it here. And then Q2 collector is connected to an RC here. Collector is connected to an RC here. There's a supply voltage here, and this is where we are taking the output, right? The output was taken here, V0. Okay, Q1 and Q2 have been fused in the sense that remove the capacitor, directly connect them together. I don't need an RC1 here. Why do I need an RC1? It directly feeds into this, not required. And then I need biasing for the base here. So what I do is I bias it like this. Here, I bias it like this here. I use the biasing here. R1, R2, and R3. I use the biasing like this here. The purpose of biasing is nothing but to set up a voltage at the base, if you recall. The purpose of biasing was to establish some voltage at the base. Establish some voltage, DC voltage at the base. So we can do that R1, R2, R3. Note that this biasing is connected to ground, so we put a capacitor here, we put it to ground here. So the two stages of common emitter and common base have been fused together into one single stage here. Oh, sorry, I missed out. So we can put here RE has to be there. RE here for the first stage here. RE, I missed that. RE, and then you put a ground bypass. All that you put here. Okay. Okay. So this amplifier, if we analyze this particular amplifier, this amplifier will give us a gain of AV equal to same minus GM-RC. Or if there's a load, GM-RC parallel RL. Will give us the same gain as a common emitter amplifier. Will give us the same input resistance as Rn equal to R pi. Rn equal to R pi. It will give us same R0 equal to RC. It's just like a common emitter amplifier, exactly same capabilities. Minus GM-RC parallel RL, Rn equal to R pi. Rn is nothing but looking from here. R0 equal to RC, exactly the same thing. But its advantage is that it doesn't suffer from the Miller's effect. It will give you a higher bandwidth. So this is what we call as the cascade amplifier. Right, so this condition, whenever you see a condition like this, that you have a connection like this, yeah, at many places you will see a connection like this, a transistor Q1 and a transistor Q2. Collector of this connected to emitter of this, we call this a cascade connection. You'll see it many places in circuits, cascade connection. Collector of this transistor C2 and emitter of this transistor, C1, emitter of this connected together. Signal from collector feeding into the emitter of the next is known as the cascade connection. So at various places you will see cascade connections. Alright, so far what we have done is we have looked at all NPN transistor amplifiers. NPN based transistor amplifiers, right? We know that there is another transistor available. This is NPN, right? We have another transistor available, which is we draw like this. Right? Should we not use PNP? Is PNP better than NPN? Well, if you compare the two transistors, NPN and PNP, first of all, let me draw them so that you become familiar a little bit about PNP. We have been doing NPN, so PNP looks like this, right? If I draw PNP, emitter is P, more like P plus, base is N, and collector is here, right? P, emitter, base, and collector. So by now you're well familiar with NPN, but note the important differences. Note the important differences. We have also seen that we are interested in active region, forward active region. Right? So if I look at my PNP, there's a diode here, the diode direction of the diode that you see here. Right? So to forward bias the base emitter junction, I need to make VBE, which is less than 0. Emitter has to be more than the base. So another way of saying it is in NPN, if I write down in NPN, remember we said between base emitter voltage VBE to forward bias is 0.7. While here what we are saying is not VBE which has to be 0.7. What has to be 0.7 is VEB. Instead of base emitter, it is VEB has to be 0.7 forward biased. Right? You have to make VEB. Base and emitter are sort of getting interchanged. And the other thing to note is collector based junction, we said collector based junction should be reverse bias. Even now it should be reverse bias. So collector based junction should be reverse bias. So earlier we used to say, well, we need to keep VCE greater than 0.2, right? 0.2 volts. Otherwise the transistor would go into saturation. Now here we will say VEC should be greater than 0.2 or more to enable it to go into active region here. VEC. So emitter to collector rather than collector to emitter. Emitter to base rather than base to emitter. So we do NPN so much that when we give you a problem with PNP, we have a hard time. We start making mistakes. The other thing that you note here is, so these are points VEB and VEC. The other thing that you note here is when you forward bias the base emitter junction, the base current comes out. IB, look at the direction of IB. Base current comes out. The emitter current is in this direction. In the normal NPN transistor, so we'll do that. So this comes out like this, and this is like this here. Look at the direction of the currents. Look at the direction of the currents. Okay, so let's basically, if this is my NPN, these are the directions of normal current here, right? Normal current here. For a PNP, normally that's why we draw emitter up, collector here, and these are the directions. No, directions of current. IC, IB, IE. Note the base current. In the normal forward active mode, the base current is coming out. This is IE and this is IC. Remember when we were analyzing this circuit, we were saying that, well, we will analyze it by assuming that between base and emitter, this is base, this is emitter, there is 0.7, and then between collector and emitter, there is a current, there is an IB here, and we said that this is equal to beta times IB. That's how we try to analyze in active region, IC. Right, this NPN transistor. PNP transistor, how will we draw? Well, we'll draw emitter like this. We'll draw emitter like this, emitter, base, between emitter and base, note the direction. This is base, emitter and base here. Base current is comes out here, IB, and there's a current here. Collector, collector current IC like this here, beta IB. Right, this is how we need to think of a PNP transistor. This is also 0.7. This is also 0.7. This is emitter node here, collector node here. This one in small signal, without drawing the small signal, this became R pi, this became GMV pi. As simplicity, without going into too much detail, this was IB, this was IC. I'm not putting R naught and all that. This is how small signal it became. If I were to draw a small signal here, what will it become? Well, there is an emitter terminal, emitter, here was the emitter, right, emitter. So there's an emitter here, there's a base here, between base and emitter again there is an R pi. The current in base current flows like this, IB, as you can see here, just the analogy. Right, this is the emitter, and we put here same analogy here. We put here we put GM V pi, and the collector current is going like this. We put here plus here and plus here we put V pi. Right? Say analogy. This one here. This here is small signal model is here, SS model is here, and small signal model is here. Now if you compare the two, compare this model here and compare this. Let me say they are exactly the same. Do you see any difference? Actually compare the two. Do you see these two? This is nothing but DC model. Is there a difference between DC model? obviously. Here base emitter voltage is 0.7, here emitter base voltage is 0.7, the direction of the currents, all those things that you are seeing here, right? But I'm saying this small signal model is exactly same as the small signal model here. The two small signal models are the same. The two small signal models are the same. Can I say that? The two small signal model is the same. Yes or no? Because remember, there's a thing that you guys should never forget: the difference between DC and small signal. DC and small signal. DC and small signal. DC is showing you the actual, small signal represents what? Change. Now in this case, note that here, in this case, can IB be negative? This is DC. Can IB be negative? It cannot be negative. Base emitter junction has to be forward biased. It has to be positive. It cannot be negative. Can IB be negative here? Can IB be negative here? It's a change, right? It's a change. Change could be positive or negative. This could be positive or negative. There's nothing about it. For example, it's a change. So, for example, if there were a voltage here, VB, if I increase the voltage here, the change is positive and the current is going up, fine. But if I decrease the voltage here, the base current would decrease and the direction would be like this. So, there's nothing important about the sign here. The change could be positive or negative. Not so in DC. In DC, there's a well-defined current. I can't have a negative current. Can't have a negative here. With that in mind, don't you think that I can redraw this circuit here? Redraw this circuit such that, suppose I reverse the value of V pi. Can I take this circuit and redraw it to be like this? Huh? And therefore what we are saying is that the small signal model of PNP and NPN are exactly the same. Small signal model of NPN and PNP are the same. DC models are different, but small signal models are the same. I can, as we said, we can redraw this. We can redraw this circuit by simply, instead of plus minus here, we write plus here and minus here, right? Instead of plus minus here, write plus here and minus here, V pi. The direction of the current source would then reverse, and direction of IB, you can always take it like this also. It's a convention, and then this diagram becomes exactly same as this diagram. All right. So small signal model of the two transistors are the same. Small signal model, SS model of NPN and PNP are same. DC models are different. That we have already seen. You have to take proper polarity of sign here, proper directions of currents here to look at the the emitter, base and collector. You have to take the proper directions, proper polarities. Otherwise, the similar small signal models are exactly the same.